ladies and gentlemen, we're going to do 9.3b today. We're going to be adding to our knowledge of tests to do for convergence. Today we're going to do the P series and the harmonic series. So we're going to use properties of both to determine whether or not a sequence converges. But before we start doing that, I would like to go back and review some of the things that we have done so far. So for our review, I'm just going to start kind of listing a series of things. The first one would be an arithmetic, oops, I spelled it wrong, only one R, arithmetic finite series. And that would mean S sub n is equal to the number of terms divided by 2. Well, that's just pretty crappy looking, isn't it? N divided by 2 times the first term and the last term of the summation. And I got a wicked shadow today. Alrighty. The next thing that we would list is an alternating sequence. Okay, so for an alternating sequence, that might mean that the first term is positive, like a positive 5, and the second term's a negative 5. This one is not going to converge, so doesn't converge. Guess it would have been easier to say that it diverges. I think I'm going to turn that light off because that's really a bad shadow. All right, the next thing would be a bounded sequence. And I just have a bunch of ideas that I kind of went through and pulled out to help us as we process through the information. A bounded sequence is a sequence that has both upper and lower bounds. Okay. Our next thing to review would be a bounded and monotonic. And remember, monotonic means either strictly strictly increasing or strictly decreasing. So that's what our monotonic term means. So if a sequence is both bounded and monotonic, then it is going to converge. Okay. The next topic is a series, which we've already talked about, an arithmetic finite series, but a series in general is a sum of partial sums of a sequence. You can start a series anywhere in a sequence. It doesn't necessarily have to start at the beginning. If I want to show convergence of a partial sum, so if I want to show convergence of a partial sum, okay, then what I'm going to do is I'm going to take the limit as n approaches infinity of my summation, okay? And then that would allow me to show convergence. The next vocabulary type word that we had was a telescoping series. And this one is a little bit different than the alternating sequence, but a telescoping series is one in which terms, I guess I should write subsequent terms, cancel out. So remember, we've done a couple of examples of these in our classwork. It doesn't have to be two side-by-side terms, but what happens is by the end of the series, most of the middle terms cancel out, and then the sum of the series becomes the first term minus, that's a B, the last term, okay? Because all of the middle terms would cancel out. Our next just reminder idea would be the sum from n equals 1 to infinity of a geometric sequence would be S sub n is equal to the first term divided by 1 minus r. And remember that the absolute value of r has to be less than 1. And then if we just add to this the sum of a finite, meaning it has a beginning and an end, finite sequence, and it does also happen to be geometric, is going to be the first term of the summation times 1 plus r raised to the n over 1 minus r. So it's really important to remember in this, this is the first term of the summation, not necessarily the first term of the sequence. R would be my common ratio, n would be the number of terms. Alrighty? I think I wrote this down. I'll check this and we'll talk about it in class tomorrow, but I think I wrote that down correctly. All right. Then we started getting our tests, our different types of tests for our convergence. So the first one that we talked about was an nth term test. Okay. And this one says, so this is our nth term test, if I have a summation from n is equal to 1 to infinity of a sub n converges, then that means that the limit as n approaches a sub n of a sub n is equal to 0, and this should be infinity, sorry. Alrighty, so if the limit is equal to 0, then that means that the series converges, okay? And then if you manage this process, I think I was actually right the first time, so sorry, I'm going to scribble a little bit more, and I'm going to write that. If, on the other hand, the limit of a sub n as n approaches a sub n, and it doesn't equal 0, then the nth term test would show that our series diverged. All right, so on this one, when we take a limit and get a 0, we know that it converges, and if it doesn't equal 0, then we know that it's going to diverge, okay? And then I'm going to write diverges. Boy, I seem to not be able to write today. That's just pretty yucky. Alrighty, so we did the nth term test. The next one that we have, what number am I on? I'm on number 10. So these are just things that we've done already. The last test that we talked about was called the integral test. And so this one has some criteria that have to be met. So the original function must be positive, which means it's going to be above the x-axis, right? Doesn't mean that it has a positive slope. It just means that it's above the x-axis. It has to be continuous and decreasing. Okay, and remember we can show decreasing by taking the derivative. Then we're going to know that the sum from n equals 1 to infinity of a sub n and the integral from 1 to infinity of f of x dx are going to, both of these guys are going to both converge, or they're both going to diverge. All right, and then we know that this is going to equal the limit because this is an improper integral, which we did in 8.8, as b approaches infinity, of 1 to infinity of f of x dx. And remember, you have to choose a value somewhere in the interval depending on your improper integral that then you're going to use to do the integration. All right, so that's all of the information that we've covered so far. So now let's move on to a little bit of new information. So we're going to get a p-series. I'm going to define both of them, and then I'll do a couple of examples. So a p-series is going to look like a sum from n is equal to 1 to infinity of 1 over n raised to the p. And if I found my terms for this, it would look like this, plus 1 over 2 to the p, plus 1 over 3 to the p, plus etc. This one has two different criteria. If p is greater than 1, then it is going to converge. If p is greater than 0 and less than or equal to 1, then it's going to diverge. Okay, so you just want to determine, writing out your terms of your sequence, if your p is greater than 1 or if it's going to be less than or equal to 1. All right, so a special type of p-series is called a harmonic series. Okay. All right, and in this one, it is a p-series with a p-value of 1. And if you'll notice, if it's a p-series, if I have a p-value of 1, that's going to mean that my series is going to diverge. Okay? And so this one would look like I might have the sum from n is equal to 1 to infinity of 1 over n to the p, and then this might be 1 over 1, 1 over 2, 1 over 3, and because p is equal to 1, then that would diverge. Alrighty, so I think what I'm going to do is I'm going to take the examples that I had down for us out of order, and then we'll go back and pick everything up by the time we're done. Alright, so our first example says determine the convergence or divergence, that is a lot of writing, of the p-series. Okay, and in this one we're going to be given 1 plus, let me scoot my paper up so you can see, we're going to be given 1 plus 1/4 plus 1 over 9 plus 1 over 16, 1 over 25 plus, and then on it goes. So then I'm going to rewrite this. So it's going to be the sum from n equals 1 to infinity. And if you'll notice, if n is 1, 1 divided by 1 is 1. If n is 2, 2 squared is 4, 3 squared is 9. So then this becomes 1 over n squared. And in this case, that means my p is 2, because if you look back up here to our formula, here's the location of the sequence raised to a power. And since p is equal to 2, this is greater than 1, so therefore we know that we have a convergent p-series. That wasn't horrible. Okay, so I'm going to put my little therefore dots in there. So therefore we know that it is a convergent p-series. All right, so then I'm going to do another example, same directions, I'm just not going to rewrite them. So in this time, our sequence is going to look like 1 over, and then I'm going to have the cube root of 4 plus 1 over the cube root of 9 plus 1 over the cube root of 16 plus 1 over the cube root of 25. So you get the general idea. So again, I need to kind of write a rule. So this is going to be the sum from n equals 1 to infinity. And then notice again, this is my position 1. This is 2 squared, 3 squared, 4 squared. So this is 1 over n squared. And this is going to be raised to the 1/3. So this is the sum from n equals 1 to infinity of 1 over n to the 2/3, because a power to a power is multiply. And then since p is equal to 2/3, which is less than 1, then we know that we have a divergent p-series. All right, so that wasn't horrible. So now let's move on into kind of a generic example. And this one just says determine if it converges. So it's going to say determine whether the series converges. All right, and we're going to be given the sum, let me scoot my paper over so I'm not quite in the dark, as n is equal to 2 to infinity of 1 over n natural log n. That looks really horrible, but we'll manage, I think. So this says n natural log n. That's a lot of n's. All right, so I'm going to look at my function. So my function is going to be 1 over x natural log x, and I want to rewrite this as x natural log x to the -1, because that's going to make our derivative a little bit easier. All right, so we know that this particular function, if we looked at the graph, okay, and then we could do some analytical work, but the graph is going to look something kind of like this, not too dramatic, okay? So notice that for n is equal to 2, it is positive, and it's going to be continuous, so we know that f of x is positive and continuous for x is greater than 2, greater than or equal to 2, my bad. So now what we need to do, because remember, one of our other tests is we need to show that the function is either increasing or decreasing. And so if I'm trying to use the integral test, I need to show that it's decreasing. So I'm going to take my derivative, because my goal is to show that it's decreasing. Okay, so my derivative, and I'm going to do it from here, so it's the chain rule. It's going to be a negative 1 times x natural log x to the negative 2 times the derivative of the inside, which is the product rule, so it's the first thing times the derivative of the second plus the second thing times the derivative of the first. Okay, and if I simplify all this, this is going to be a negative times 1 plus the natural log of x over x natural log of x and then quantity squared. So there's my derivative, okay? I could set it equal to 0, but if you'll notice this right here, the natural log of any number larger than 2 is going to be positive. And so even if this is negative, right, and this is positive, and I square it, this means that my function is always going to have a negative slope, which means that it's decreasing. So I'm going to say that f prime of x is decreasing. So then that means I can use the integral test, because I've met the 3 criteria. And my 3 criteria were to show that it's positive, to show that it's continuous because there's nothing down here that's going to make it undefined, for x is greater than 2, greater than or equal to 2, right? And then we found out that the function is actually decreasing. So the integral test says I'm going to do the integral from 2 to infinity of 1 over x natural log x dx. So I'm going to let my u equal the natural log of x. My du is 1 over x, that's supposed to be a d, dx. So my integral becomes 2 to infinity of 1 over u du, which is the natural log absolute value of u evaluated from 2 to b. So this is going to be the natural log of the natural log of x, and then I'm going to evaluate from 2 to b, and then I'm going to take the limit, okay? So I'm just going to go ahead and take my limit since I'm doing the integral test as this is written. So this is going to be the limit as b approaches infinity of the natural log of the natural log of b minus the natural log of the natural log of 2, okay? And then if we looked at this math, we took our limit. This is a constant, so when I take the limit, this guy goes away. And then we'll see that, and I would probably have to use L'Hopital's rule to get my limit. We're going to say that the series is going to approach infinity. Therefore, the series diverges. Gosh, I cannot write today. I'm sorry. Whew. All right, the wind must be scrambling my brains outside because it's blowing like a hurricane. Alrighty, that is actually it for today. So this process you would have to work on a little bit, but this is a constant, so this goes away. And then I could do L'Hopital's rule or whatever I wanted to come up with the limit of this guy as b approaches infinity. So we're adding one more test to our, actually it's not really a test, but it's just kind of process. We added another process to our list of tricks for our series. Alrighty, that's it for today. I will see you tomorrow.